This PowerPoint goes along with the game of Electron Battleship. However, its main objective is to explore the topic of electron configurations. We will determine what they are, what their components are, and other important information. This is a Purdue PFDD EPICS operation with support from the National Science Foundation. What is Electron Battleship? It's a game. It works in pretty much the same way as the traditional Milton Bradley Battleship game, with slight differences. To watch the game in action, click on this link, which will take you to our YouTube page. The game uses user interaction and repetition to grasp the dreaded concept of electron configurations. If you are new to electron configurations or trying to refresh your memory, Electron Battleship can help. First off, what are electron configurations? They essentially map out the location of all the electrons in an atom. They are analogous to quantum numbers, but are more easily visualized. Basically, electrons can be assigned to a specific spot in a specific orbital, in a specific sublevel, and a specific energy level. For example, let's look at the configuration for fluorine. The number in front of the letter represents the energy level. That number, along with the letter, which we will later learn represents an orbital, makes up a sublevel. The number in the subscript represents how many electrons are in that energy level. So we can see that fluorine has 9 electrons, 2 in the 1s sublevel, 2 in the 2s sublevel, and 5 in the 2p sublevel. But where do the sublevels come from? We'll see in a bit, but before we get into that, let's look at what orbitals are. Orbitals are regions of space around the nucleus of an atom where an electron spends most of its time. Basically, if we could reach in and grab an electron from that region, we'd have a 9 in 10 chance of actually getting one. Orbitals are used to describe the position of an electron in an atom since we can't know the exact position. This is because electrons are too small and easily manipulated by any instruments we might use. For more information, see the Heisenberg uncertainty principle. Anyway, there are 4 kinds of orbitals: s, p, d, and f orbitals. Each orbital can only hold 2 electrons due to the Pauli exclusion principle. S orbitals are spherical. However, as the energy level is increased, the size the s orbital gets in that energy level is bigger than an s orbital in a smaller energy level. Another important thing to know is that there is only one s orbital in a sublevel. Using this fact, and the fact that an orbital can only have 2 electrons, we can conclude that for a given ns sublevel, where n is the energy level, there is a capacity of 2 electrons. Next up are p orbitals. They are in the shape of an 8 on its side. An important difference between s, p, d, and f orbitals is the number of each that is present in a sublevel. While there was only one s in a ns sublevel, there are 3 p orbitals in an np sublevel. As you can see in the picture, there are 3 types, which are discernible by their orientation in a graph. And since an orbital can only contain 2 electrons, an np sublevel can hold at most 6 electrons. The shapes of d and f orbitals are complex, but you don't need to know them to understand the concept. What you do need to know is there are 5 d orbitals per nd sublevel, thus 10 electrons per nd sublevel. And there are 7 f orbitals per nf sublevel, thus 14 electrons per nf sublevel. If you haven't noticed, there is a trend at work here. ns sublevels have 1s orbitals, np sublevels have 3 p orbitals, nd sublevels have 5 d orbitals, and so on. A good way to remember this is that it increases by 2. And since there are 2 electrons per orbital, the number of electrons that can be in a sublevel increases by 2 times 2, which is 4. So now that we know what the configurations represent, how do we go about determining them? A good starting point is to realize that the number of electrons in an atom is equal to the number of electrons expressed in the configuration, since the configuration is just a mapping of the atom's electrons. Take oxygen, for example. It has 8 electrons. If you add up the numbers in the subscripts of its configuration, 1s2, 2s2, 2p4, you get 8 electrons. This is also a good way to check if an electron configuration is right. As you have seen, just knowing the number of electrons does not really help us. We must be able to place them in the appropriate sublevel. Sublevels are just ways to describe an electron's position in an energy level. As an analogy, think of an energy level as a house. A person entering a house is the electron, and the different rooms of the house are the sublevels. What determines which room or sublevel the person/electron will go to? Well, it depends on the energy of the sublevel. Electrons enter sublevels in order of increasing sublevel energy. These energies are found through experimentation. Take a look at the picture. Electrons will fill sublevels with the smallest energies first. Generally, as you increase in an energy level, you increase the energy of a sublevel. However, there are important exceptions. Let's look at the table again. Electrons will fill a 1s sublevel first, as it has the least amount of energy associated with it. Then it will fill the 2s and 2p sublevels. Then the 3s and 3p. And then the 4s. But then notice the next highest energy associated sublevel is a 3d sublevel. First of all, not all orbitals are present in every energy level. There are no D's or F's in the first or second energy levels. However, D's do show up in the third energy level and in every following one. However, the 3D sublevel has a higher energy. It requires more energy for an electron to reside in it than a 4s sublevel. F orbitals show up in the fourth energy level and have higher energies than the 5s and 6s sublevels. This probably seems confusing, but there is a wonderful tool at our disposal to help: the periodic table. Pay close attention to where the letters S, P, D, and F are. As you can see from the previous picture, electron configurations relate closely to the positions of the elements in the table. Generally, each row of the table represents an energy level, and columns represent sublevels. For example, elements in the first and second column fill S sublevels. Elements in columns 13 through 18 fill P sublevels. Transition elements fill D sublevels. And lanthanides fill F sublevels. Let's do an example. If I want to find the electron configuration for carbon, I would first locate it on the periodic table. Then I would start counting from the beginning of the table at hydrogen, the full sublevels. Hydrogen has its electrons in the 1s1 slot, and helium has another electron that fills the second slot to make 1s2. So we say 1s2. Then we move down to row 2, which represents the second energy level. Lithium has one more electron than helium, so it has its 1s2 along with the 2s1. And beryllium has one more, so its configuration is 1s2, 2s2. So 2s2 would be our next term. To get to carbon, we need to add 2 more electrons. These electrons will come in the 2p sublevel. Since the 2p sublevel has 6 slots, we will only fill 2. Thus carbon will have the 1s2, 2s2 that beryllium had, plus a 2p2. So carbon's configuration is 1s2, 2s2, and 2p2. It is important to remember what was said earlier about the ND and NF sublevels. The ND sublevel starts at 3D, not 4D, even though the elements are in the fourth row. As you go down the table, the n number increases by 1. The same holds for F. NF sublevels start at 4F, even though the elements are in row 6. This occurs because of the energies of the sublevels, as stated earlier. For example, the electron configuration for gallium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1, not 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4d10, 4p1. And the electron configuration for thallium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6x2, 4f14, 5d10, 6p1, not 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then a 4 or 6, f14, 5d10, 6p1. Check the periodic table to see if these make sense. As you could see with the previous examples of gallium and thallium, the configurations can get pretty lengthy as you progress down the periodic table. To shorten them up, a noble gas configuration is sometimes used. All it is a kind of shorthand. The configuration is the configuration of the valence electrons tacked on to the end of the configuration of the closest noble gas. For example, gallium has a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. The configuration of argon is 1s2, 2s2, 2p6, 3s2, 3p6. Thus, the noble gas configuration for gallium is argon, 4s2, 3d10, 4p1. As with anything in science, there are exceptions to the pattern of electron configuration. Please note that the configuration of chromium is argon 4s1 3d5, not argon 4s2 3d4. And the configuration of copper is argon 4s1 3d10, not argon 4s2 3d9. This is so because the 3d4s sublevels have very similar energies. Also, there is a slight increase in stability with full or half-full sublevels. We hope now that you have a better understanding of what electron configurations are and how to determine one. Now use your newfound skills to crush your opponent. Enjoy!